you, Dr. Patrice Bayer, for inviting me to come here to PIMM, and I think for Penn for inviting me for this talk. So yes, my name is Jay KEIST. I'm at Penn State in the Applied Research Lab at Penn State, and I decided to give a talk on our current work on functionally graded materials, metal-based materials, by additive manufacturing. So just an overview of this. I tried to keep my presentation fairly open, but if you have questions, please, if you need to, you can ask during my presentation. But I'll go through kind of an introduction, give coordinates myself, where I'm at with Penn State and our additive manufacturing consortium at Sim3D. Then I'll give you a background on functionally graded materials, and then I'll go through my personal work with the functionally graded materials several years ago, trying to figure out how to do this, and then our current research directives with the 2 PhD students I have currently, and how we're going to try to improve upon our functionally graded materials. So just for the introduction of where we're at. So I'm a research professor at Applied Research Lab, and the Applied Research Lab is within Penn State, and it was established after World War II. The idea is that we were going to do, the lab was set up for help with research and for for Navy applications. So initially, the Applied Research Lab at Penn State had a history of working with submarine technology. Since then, we've grown into all areas from communications, new and different organizations as well. And I'm in the materials and manufacturing side, dealing with additive manufacturing. And so that's where my location is in the Applied Research Lab. It is the largest research unit at Penn State. Penn State's a relatively large school in university, in the United States. And our research lab has over 1,400 faculty, students, and engineering and staff. And our expenditures are fairly large for that. We typically over $300 million per year. And since 1996, we are designated as a UARC. I don't know if you understand what UARC is, but it just means that we're a trusted research organization for U.S. Department of Defense. So within that Applied Research Lab, I have a small group. I have a group of 6 engineers, 2 staff, and 2 PhD students currently. And my group is dealing with characterization. We have materials evaluation and characterization. So we have a few SEMs within our lab. We have a X-ray CT system, and we have some non-destructive testing in our lab. But most of our focus is on characterization of metal-based additive manufacturing, but we're also dealing with ceramics as well. And most everything we do is laser-based, but we do have some binder-based systems in our lab as well. But the main structure is we're doing with process structure, understanding how process changes structure and how that structure changes properties. And as I mentioned, we do have a non-destructive analysis within our lab as well. Now, just to make it confusing, but we are also part of the Sim3D, and that's the umbrella organization at Penn State for all additive work. Sim3D stands for the Center of Innovation Processing through Direct Digital Deposition, and it is set up by the Additive Manufacturing Lab and also 2 colleges, the College of Engineering and the College of Earth and Mineral Science. So all 3, 2 colleges in applied research run this lab, and it's a multidisciplinary. And this figure on the left is supposed to give the idea that we try to work on everywhere from basic science all the way up to the applied nature of getting that basic science out to the industry and department as needed. So in Penn State and Sim3D, there's over 40 professors that are affiliated with Sim3D. They range from various departments, from industrial engineering, computer science, material science, mechanical engineering, aerospace, and we even have professors that are dealing with the business side as well, and under Sim3D. It is co-directed by 3 people. My colleague Ted Ruzzo is also Applied Research Lab. Tim Simpson is in mechanical engineering and industrial engineering. And finally, Professor Mike Hickner is in material science. So those are the co-directors of the Sim3D. As far as location, Pennsylvania is on the East Coast. We're in the middle of Pennsylvania. It's a land-grant institution, meaning they just plopped it right in the middle of Pennsylvania. But we're strategically located near other large cities, even though we're in the middle of nowhere. So we're near 3 hours, 3.5 hours from New York City, 3.5 hours from DC. Everything's 3 hours away from us. And Pittsburgh. We do have our systems currently. We have several directed energy deposition systems. So we have a DMG Mori, which is a hybrid system with directed energy deposition with the ability to machine. We also have our own home-built large deposition system. It's a laser-based with 12 kilowatt laser that can do both wire and powder. We have our own Optimic. We have an old Optimic system back from 2006 or 2007. It's an MR7. And then we had our own homemade, just to make a larger envelope, similar to the Optimic. And then as far as the powder bed systems, we have an EOS and 3D systems. The 3D systems at 30, they're roughly about 11 inch, excuse me, I get a pardon. I'm from the US, so I'm always thinking in inches. So roughly about 30 centimeters, 3,000, I can't remember the transition, but it's roughly about 24 centimeters on that as far as the build volume. And then we also have some additional things, like I mentioned in our lab. We have an X-ray CT. We have a ferro arm for dimensional tolerances. We do have an X1 M1 lab and a new Innovent system for ceramics. And then finally, we have a very old Stratus machine that we use for polymer. We do have some new capabilities that came on this year. And that's the Factory 500. That one's easy because it's 500 millimeter build volume. We just started up a wire arc additive manufacturing. So instead of laser based, this is our first arc based welding process for additive. And then another group in ours does a lot of cold spray. So we have an additive cold spray option as well. So these are just new things that came on. So that said, I'm going to go in the background of what functionally graded materials are. And as far as what functionally graded materials are, you're designing for a particular application where you're trying to take advantage of two different material systems. It's typically done within spatially two different material systems, but you can also do it microstructurally within the same material. And you're doing that variation of across a direction. So that's why the functionally graded material comes in. It's usually, as I mentioned, done by adding two components together where you're trying to harness the benefits of both in your system. And the concept was first considered back in the 1980s. And it's usually, first it was done by thin film applications, but now they're doing more. What Additive is doing is like what they consider bulk applications. FGMs also occur naturally. I point out that, you do see it in bones, you see it in structures like in bamboo, and you can see in the structure on the left. The idea is like this, in this case, you're just a bamboo, the pores kind of change depending on how close it is to that edge. And that's basically what the functionally graded material is, changing spatially. So why functionally graded materials? It really comes down to trying to minimize the differences between those two materials that you're trying to adhere. So you can just do it like a cladding, or where you take a material directly deposit onto another material for, like, say, corrosion resistance. But that cladding has a weakness, which is at the interface. So the idea with the functionally graded is you can take that interface and extend it out. And that allows you hopefully better adhesion, and that cladding layer, that protective layer, be able to stay on your part longer. It also should help reduce interfacial stresses, especially if your component goes through cycling. So it's an example of aluminum. Alloy is a cast in alloy 336, which is cast with a aluminum ceramic. And this is the interface that they did by grading using the casting process. And this is where it did. It was just a flat the Duraclam right on top of the aluminum silicon. And if they cycled this, and they can see that, it broke just because the thermal expansion coefficient between these two are so different that it causes some stresses that ended up breaking. It also, the other thing is that functionally graded materials allows you to customize. So you can think of having, for automotive applications, you can have areas that that you'd like to have break. So you can have design strong and weak areas within those parts. That's another option. And then you can change other things like densities and thermal conductivity as well. There are ways to classify functionally graded materials, and this just gives an example of like all the ideas you can think of. You can have it, typically we're thinking of functionally graded, have a gradient between two materials. You can also just try to do without, like I said, like a cladding layer. You can also get very, you can try to do things like, we use this actually for damping applications where you're trying to dampen. You can do 2 different materials, one for strength and one for damping. And then you can even think about it, and this is, I'll talk about it more, is adding even 3 materials together to try to transition from 2 materials that just don't play nice together. You can also think about it, functionally graded materials as, this is the gradient where you have 2 different materials put together. But you can also think about it as size, you know, either orientation, where you can change the orientation, which often happens in carbon fiber, or you can do size, you know, maybe it's pores or maybe composite, and then as well as, excuse me, this is shape and as well as size. So with that, additive manufacturing has become kind of a tool to make these bulk functionally graded materials. Initially, they were done by powder metallurgy or centrifugal casting. Those are kind of difficult processes to get very tight control on your final component. Additive manufacturing, the benefit is, since you're dealing with this as a layer by layer approach, especially with laser direct energy deposition, you even control the point where you're depositing material. You can also control the material that you're introducing that well pool. So for what I'm talking now, when I talk about additive manufacturing, I'm talking about this direct energy deposition. And that's where you're either supplying the material as a powder or a wire, typically, and you have a heat source, which in the case I'll be talking about today, it's a laser. And you're doing still a layer by layer process for additive, but the benefit is that you can change that feedstock that you're putting into that well pool. And this is some examples here that was built by laser deposition, one by Alison Beasley in our lab here, showing with a 316. So now we'll go through kind of our initial work of functionally graded materials. I just started at Penn State. I started at Penn State now 8 years ago. And one of my first projects was trying to build a functionally graded material. And it was a kind of success, but kind of a failure as well. So it was brought up to us that Sandia was looking for ideas to bond titanium components to aluminum components within space applications. One thing apparently about space is you can't have gaskets that are organic in nature. They want to try to get rid of organics because those can degrade with the radiation that structure receives in space. But there is some thermal expansion that occurs when the satellite moves in and out of the sun. And those thermal expansion is hampered when you try to combine 2 light materials, one titanium and aluminum. Together, the thermal expansions are quite different. So that's why they're coupling ideas between titanium components and aluminum is to try to match up that thermal expansion behavior, where the titanium doesn't really grow that much when it heats up, but the aluminum does grow considerably. And so that was our initial thought. Like, okay, great, we can make a coupling where we build one side as aluminum, and then we slowly grade over to a titanium alloy. And that was our initial issue. And so we got 2 materials. We just used a Ti-64 prep powder. This is a powder that's made by the prep process, nice spherical. And then we modified a cold spray apparatus at Penn State to try to make some 2219 powder, aluminum alloy. This is an aluminum copper alloy that's used for welding. It's known to be a very good welding alloy, and plus that it's heat treatable, so we can get high strength to get the strengths that they were requesting with Sandia National Lab. And so we had an old Optimex system. Here it is showing right here depositing titanium. And it's an old, like it's meant from 2007, it's still a major workhorse, course, using just a 500 yttrium doped fiber laser. We're processing around 460 watts. And we deposited from aluminum. We tried to initially deposit aluminum on top of titanium. And so we made some walls, very simple walls, but if you actually took a look at inside of them, they were just filled with cracks. And so this is something that we immediately saw that what can we do? And the issue is those cracks extend very close, basically right to the Ti-64. So this is the Ti-64 base plate. And the minute that we're adding aluminum, you can see the cracks just start coming in. So even though we're fine here, it just seems like, grading with an aluminum alloy on titanium is probably a no-go that we can find out. And so what happens when you think about grading is the fact that I think a lot of people, especially they get a sense, it's like, well, we can grade from one side to the other, but they forget the fact that you're seeing all these intermetallics, that these intermetallics are brittle. They have a different thermal coefficient than what you typically are in. So like from an aluminum to a thialuminide and then another thialuminide. So this is why we're having trouble. And I would just mention, thialuminide, especially this one, that's actually a additive manufactured alloy, but they're doing a different process. They're using electron beam typically, and they're just staying within that particular system. So in order to get something out of this, we at least decided that, well, we don't have much room here to move. We saw that immediately, but we do have some room here. So let's start with the aluminum alloy and see if we can build up as close as possible to that titanium aluminide. And that was relatively successful. We did a grading structure, and then we were able to build our process pretty well. And the idea is that we would take then this plate. This was a aluminum copper alloy plate in 2024. We put on that welding alloy first, and then we grade up to a titanium aluminide composition. And then we were able to machine that out and use that for, send it back to Sandia so that he could do thermal cycling with it. We did have a few defects because we didn't have too much funds to try this out. But these defects weren't really related to the problem with the composition. It was the problem with our processing side. We had a stall in our Optimix system where the powder clogged the nozzle. We had to stop and restart, and it left a mark here on that area. The other issue is when we made the top, it wasn't exactly very smooth. I can go back here, and that little area that was causing a little bit of issue with our ended up showing up some cracks here that we just couldn't machine out. We did look at a wall. One we sent over back to our sponsor, but one we were able to keep. And so we did some microstructural analysis. Overall, when we built this on top of this aluminum 2024, it had pretty good bonding. We didn't see any gross porosity in it. We didn't see any cracking, so overall it looked pretty good. And here's our fusion area. These are just optical microstructures showing the rocked 2024. Here's our weld and a little bit of heat effective zone. And then as we're transitioning up in this area, we're starting to add titanium. And we can see immediately the titanium acts as a grain refiner. But besides from that, it's actually worked pretty well. But then if we go straight to the top, when we got into the titanium aluminide area, we also saw a relatively interesting microstructure. You can see on SEM where the titanium aluminide forms this medium gray structure that takes over roughly 87 or 90% of the volume. And then the aluminum that's left over is in between this dark gray. We did, like I mentioned, this is a copper alloy. We will see the aluminum copper phase coming out here as a white. And this is a backscatter electron image. So the heavier the copper, that's why it's showing up as white. But overall, it looked pretty good. And then we, just to test how good we are, which this is our failure, I'm afraid, is we took a dilatometry sample from the material that we made. We ran it and compared it to Ti-64, which is what we were trying to get to. So our thermal expansion for Ti-64 is roughly about 9 microns per meter centimeter, or excuse me, Celsius. And then here's our 2219 that we used on the other side. We were able to reduce it a little bit, but we're nowhere near where we would like to be. So although we were able to use that titanium aluminide to get the thermal coefficient down a little bit, thermal expansion coefficient wasn't really enough that Sandia definitely was looking for. But with that said, maybe we can look and try to modify both sides, titanium as well. And there is some work that was done adding copper to titanium to try to increase the thermal expansion coefficient of that. Here's another, I want to call it failed, but this is my colleague, Alison Beasy, Professor Alison Beasy. Her first work as well in trying to look functionally grade material. We did these about the same time. So she tried to do Ti-64 to NVAR. The benefit of NVAR is it shows very little thermal expansion. It's almost zero. And then the titanium has a little bit, but NVAR is very heavy. So let's say we can combine the fact that we can get a component that shows very little thermal expansion in one area, but we have the lightweight strength of the titanium on the other area. And that's the benefit of going after this. And this is work that some BZ directed with her students. But when they tried to build theirs in the same system as ours, they had some major cracking as well. Same thing that we saw. So what happened is they built up the Ti-6-4, and the minute that they started adding iron, which is the MVAR, is mainly iron and nickel, that they started seeing cracking. And so probably the same thing that occurred to us, they happened to them. So you can see that here, these are the ternary diagram for at 1273 Kelvin. And here's the titanium, and this is the nickel and iron. They're trying to go across here, and you're hitting these intermetallic regions right here. And you can see it right here. So you go start with a titanium phase, and then immediately goes to 100% of this intermetallic phase, which is an iron nickel Ti-2. And again, there's another one here. So it just broke right there at that area. But if you want to read more, they did write a paper on this and trying to point out the fact that CalFad works, SHIO maybe works better, and there's some interesting things that they really will pull out, at least on the modeling side of that work. So with that said, I'm going to talk about our current research direction with my 2 PhD students I have currently. Trying to take advantage of what we learned from these failed experiments and move on to see if we can get a better idea of how to create these functionally graded materials. One is on the design side and process planning side, but also dealing with new prediction tools as well. And then I also go through it, and one of our students working with creating a high strength steel to another student. So, as I mentioned, we're trying to learn from our mistakes. And one of the 2 areas that came up that we really felt like we needed a process planning for DED of functionally graded materials. Basically, you're asking to change the material on the fly. And the benefit is of additive manufacturing is you can do this layer by layer. You can design where you're putting your material down, and that in turn can design where your grading goes. But in order to do that, you need to make sure that the laser system and the power delivery system is able to compensate for these changing material types. So if you're mixing 2 materials together, like a titanium and a slightly lighter aluminum, or a titanium with a slightly heavier steel or Inconel, you need to be able to adjust for both the power, the feeding rate as well. And that ensures that you're depositing what you want, you're remaining dimensionally stable. So if you're running you're assuming that you're getting a bead height of, let's say, 1 millimeter, you want to be able to maintain that all the way across, no matter if you're depositing material A, a mixture of material A and B, or material B by itself. You always want to make sure that your overall process is consistent and your dimensions are consistent of that bead geometry. And then the other thing you want to do is account for dilution. So if you're trying to hit certain targets and maintain a chemistry within certain limits, it's important to understand that dilution level as well. So that was one area that we felt like we needed to concentrate on. The other area that we wanted to concentrate on is like trying to develop new predictive tools. So it's one thing to take a CalFad database and say, I can run with this. And it's not like you can tell whether or not you're going to have failure or not. You can see that you hit some intermetallics, but some processes can run with intermetallics without a problem. But the idea is, can we build upon this CalFad database to figure out what are the problem phases that we need to avoid, and then we can try to deal with that. So that's one area. That's the second area we're trying to do, is try to build CalFad database and also develop these tools to rapidly assess functionally graded material design by the constituents, and possibly the goal would be to chart, let's say we're trying to do a difficult one like an aluminum to titanium, we can maybe chart past using chemistry to chart past around those phases that are going to cause trouble and cracking. So first project I'm talking about is my student Fred Leah. I'm co-advising with Dr. Sanjay Joshi, industrial engineering, and this is the process planning for additive manufacturing metallic functionally graded materials. So the idea is to demonstrate the capability of an advanced control system for directing and deposition for making these functionally graded materials. The challenge is what we're trying to do is to deliver what we designed and to avoid these brittle metallics that I pointed out that causes these issues. And then understand the impact of how does remelting occur, and we wanted to be not, a lot of times we're building a lot of walls and we're thinking very much in one-dimensional direction. But we also wanted to think about, three directions. What happens if we change composition as we go up and then we move to another area and we change composition there. So we're trying to understand how that remelting and the effect of that remelting on dilution impacts our final chemistry and gradient. So the issues that we wanted to address in this project, and this is a kind of a schematic of what we're dealing with, is the direct energy deposition where you have two powders, and this is the easy case where we had aluminum or titanium are trying to put together and deposit. And so the main thing is, how do we successfully vary the process, as I mentioned, with the fact that these powders are going to change and absorb how it absorbs the laser power. It's going to, the melting temperature probably changes, the viscosity of this material changes, and conductivity can change. So all those things impact your final process of that material. And so the thing is, we wanted to be able to successfully vary the processing conditions with that varying feedstock. The other thing we want to do is assure that we have consistent melt pool geometry as well. And again, that applies like, how do we make sure we feed with a varying powder? How do we make sure we feed it correctly to the melt pool? And assume that, can we always assume that we get the same volumetric flow rate of that material, despite changes in density to the from the feedstock to that melt pool? So that's kind of our research direction. And then our objective is to build two models. One is just a simple energy balance model shown here on the right. I don't want to go too much into this, but the idea is that the power coming in, your efficiencies, and your heat capacities, conductivities, and from this you can get a sense of how deep your melt pool is going to be, and you can get a sense of how large your melt pool is going to be by using these things, these constants for the powder. And then all you do is you change that depending on what you're trying to change. So if I'm having aluminum, I'm adding titanium, I just modify these density, heat capacity, and thermal conductivity as needed for that. And then hopefully I can use this as a predictive tool to help understand, how do I need to run my process? What power do I need to run? What speeds do I need to run? And how does my powder flow rate be? The other fun thing we want to do is a simple dilution model. And I'll show here, the dilution model is just a geometry model. We're assuming that we're depositing a material of a certain composition. Part of that is going to be diluted to the material underneath it. And so we're just using geometry to figure out that dilution model. And the plan is then to take that geometry and then build it upon, as I mentioned, not only one direction, but also in two directions as well. So both the build direction as well as lateral direction. And so this is the energy balance model, and this is the kind of the dilution model. And so we built two test cases, and we decided to do, there's no reason to do 316 with this is NAB, is a nickel aluminum bronze alloy. So it's a copper containing alloy with nickel aluminum. And we're trying to grade it with a 316 stainless, which is mainly iron and chromium. And so we did two types of builds. One, we did a vertical, so we built a very simple wall. And the other, we did a horizontal transition. And so the idea is that we can start looking at how we did the vertical, understand what happens to the chemistry, and see if we can get that to correlate to the model that we built. The same as so this was built vertically, a simple wall, and this one is built like a cladding layer right on top of the stainless steel. So we started with NAB and moved back to the stainless steel. You can see some issues here that we found, is like some cracking right at the stainless steel, which makes sense because stainless steel can be problematic when you try to add, especially nickel, into the system. So it actually becomes prone to cracking. And again, so right now we're in the phase of doing characterization. My student is trying to understand the characterization and bring that back to the model, modify the model, and hopefully we can have a control structure that we can use, that we're hoping to use for our future functional graded materials as well. So that kind of finishes that up. And the summary to date on that project is that we think we got a decent, simple energy balance model to help predict the melt pool and penetration depth, and allows us to understand how the remelt size is impacting our part. And then we also hope that we have a dilution model that we can use to predict how our composition changes, not only in the build direction, but also if we're trying to do the lateral direction as well. Right now, these models being verified by detailed characterization of these test cases that we made. And the goal is, actually, we're trying to build like a map. At least for, this will be our test case map, but the idea is that we can build a map for other material systems as well. And that goes into kind of our next project, which my student Colbert just started this summer. And I'm working with Professor Allison Beasley and Zikwai Liu, both in the material science department at Penn State. Allison Beasley is a more mechanical driven material science, and Zikwai Liu is in CalPad and DFT calculations. So the project that we're trying to build upon Fred's work, which is on that process control, is to use that process control to develop a puncture graded material of a high strength steel. This is an Air Force alloy that was just recently developed to a stainless steel. And the idea is that we can kind of bridge together two different material systems, one very high strength and the other with corrosion resistance, that we can then make some samples that we can take a look at and understand the mechanical behavior. That was the goal. So the Air Force alloy is one of the highest strength alloys for steel. It's over, the tensile strength's over 1,500 megapascals for the tensile strength. It still has good elongation of over 10%. It was developed primarily as a weapons alloy, and it was just developed about 5 years ago. So material is like a little bit hard to come by. So we have some very good powder, but we don't have much. So our samples right now are a little bit small. But this was our just first attempt of doing a grading. We did both a kind of our gradient, where we tried to put a distance between the deposit Air Force 9628 alloy up to the stainless steel. And then we also did a bimetal grading as well. So we basically went to the Air Force and then cladded right on top of that in stainless steel. The idea is that we'll build upon this so that we can build some tensile bars that has some unique geometry within that grading seat, and then we can do some imaging, understanding the strains as it goes through tensile. So this is the kind of what we're trying to do, develop an understanding of how the gradients affect local solidification behavior. And we're trying to also use CalPad to understand if there's any phases that we need to be worried about. This is the chemistries that we're dealing with. That Air Force alloy is a carbon steel. It's an low alloy steel, and it has 4 constituents that does that hardness. There's a chromium, moly, manganese, silicon as well, nickel. So all these things play in that strength of that alloy, and we're doing it to 316. And so we're keeping a lot of these constituents there. The only thing that we're doing is that we're going from a chromium. The only thing that we're possibly doing is removing that carbon. But overall, this is why we chose this alloy, because it looks like it should be a fairly simple alloy to make, and we shouldn't have any problems or issues that come up. This is our initial CalPad analysis, and you can see this is the steel side, high strength steel, and this is stainless steel. There's really nothing in between, so we're not hitting any instrumentality issues, and this is just a blow up of this region right over there. We do change our what we think our solidification behavior is. So we're moving from a martensitic, as expected, to an austenitic or to ferrite. That may cause an issue with solidification cracking. And so we're trying to figure that out. And so as we're moving over from, the steel side, which is going to be definitely a ferrite solidification mode, to an austenite side, sometimes there is a transition issue that we see here that we can get some cracking. But luckily, so far, we haven't had that issue, which is when that austenite and ferrite come together, that may cause some issues in terms of solidification cracking. We just started analysis of this, and so this is just, sorry for the presentation, but this is just basically a few weeks old that he was able to do some XRD on our graded structure. And as expected, here's our Air Force alloy. It looks very much like a BCC structure. So we don't know quite yet if we have a martensitic structure yet, but we're going to do additional testing. But you can see as we go up the structure, we're losing that peak, and then we're gaining peaks that are on the austenite side as well. So this is for 100% steel, and then as we're moving up to 100% stainless steel, it's progressing as we expect. And we've done some quick EBSD and compared our phase analysis this is the austenite that we're seeing. We're, definitely at the, at the Air Force alloy. This should, I got this backwards, my student. This should be 100% ferrite, and then as we're moving up, the ferrite just decreases or go up to the 316 and becomes mostly austenite. So this is austenite is in red. This is the blue is the ferrite. Ferrite / martensite. We don't know quite yet if it's what we have. And then as it moves up to austenite. And then this is just the inverse pole figure color map, so that EBSD data to show the fine structure that we're seeing. And then it actually looks fairly fine in grains. And then we move over to almost a columnar grain as we move up to the stainless steel. And it actually does look very columnar as we get into that stainless steel. So that's kind of our summary today. This project is just starting. So the bit we're trying to move over to testing these, building some samples and run some DIC tensile testing. This is an example of another grade structure, but instead of trying to degrade in the in the y-axis in this case, we're going to make samples where we're grading in the perpendicular to our pole direction, so that we can put in like a cord structure. So that's the plan. We're going to put the high strength steel in the center and stainless steel on the side and try to figure out how that graded structure impacts our string. And we'll be doing that for both the bimetal, which means we try not to have a gradient, and then one with a gradient, and see how that impacts our strain behavior during tensile testing. So checking time. So with that, I'll finish off with the last thing that we decided we needed, which is our predictive tools. And for this, we're collaborating with Professor Zikwai Liu at Penn State. He is kind of on the forefront of DFT calculations, CalFAT calculations for understanding phase analysis chemistry. And so I'll just finish with a few slides from Zikwai Liu and understanding what his main drive is in trying to support not only additive manufacturing, but also other new tech processes such as high entropy alloys. He's been on this work for a long time. He's on the initial materials genome back in 2002, trying to support building databases for understanding how how chemistry and processing impacts your material properties, phases as well. And so from all these things, they basically come up with new ideas like accelerating transition back in 2004, bridging the valley, materials processing for defense orientation, then integrating these computational material engineering for using CalFAT software to import and integrate it to materials engineering. And then finally, his latest adventure is working with the materials genome initiative that started off in 2011 and trying to bridge all these things together, where you're trying to get experimental tools, computation tools, digital data tools, and build it into an overall work system. So make sure to back. So as far as the data ecosystem, excuse me. The idea is that you can take your data, you're getting data all the time. You have the proto data, your DFT, your CalFAT, your analysis of the material. You help build that CalFAT database. That CalFAT database then can be used for your material services, like your design or of material. Then hopefully everything is able to, as you building material services, that helps understand your underlying physics. That helps further refine the CalFAT data. And then hopefully the main thing is you're able to help refine that process as well. And so that's the idea of what the genome initiative is. And so the idea is to take this, and so that we, when we do CalFAT, we're always running into the issues of databases. We don't have the database, or the database don't play nice together. You have an iron database or copper database. And if you try to put those together, you end up with really not really very good information. So the idea is to use these new tools to kind of bring all these different materials together, so you're not worried on the database side. And so these are some Zikwai's tools that he gives that maybe you can find interesting. The idea is to bring in high throughput, uncertainty to quantification, and make sure that you can do this. So this is the data generation, machine learning, data processing as well. So these are the tools that Zikwai is also very much hands-on on that side. So we're trying to collaborate with Zikwai on the functionally graded materials and see if we can build on his materials genome database. Because that's one thing that we're dealing with functionally graded materials, is that we, databases that we rely on don't act well together. And so how do we bridge like an aluminum database with a titanium database? Or how do we bridge a copper database with a steel database? So these are the things that we're dealing with constantly. So there are some workshops as well that ZPI has been part of. It's part of the Materials Genome Foundation. So, but that said, my final thoughts on functionally graded materials. So there's, functionally graded materials hold a lot of promise. Definitely, and for space applications, for applications for corrosion resistance, for applications where you're trying to deal with materials with dissimilar thermal expansion behaviors, or you're trying to add reduce weight while maintaining strength. There's a lot of promise. But at this time, if I was to take a personal look at it, functionally graded materials in this bulk form, I feel we need to think small first. So in reality, we just don't know enough to bridge these gaps of a lot of these systems. So think small, look at phase diagrams, avoid intermetallic regions, and choose, and the easy thing is choose compatible systems. For instance, my student is looking within the iron system completely. It's just doing a high strength steel to stainless. Another option, which I showed you, what we ended up doing, we just stayed with the aluminum system, where we went from an aluminum alloy, a copper containing alloy, to aluminum composite that aluminum titanium, titanium aluminides in it. But on the other side, we still want to develop these predictive tools, and that's where the CalFab, getting the databases, DFT analysis, building the CalFab database beyond the usefulness that it has. And the goal would be then, well, I can have that database chart my way from, let's say, my aluminum alloy to my titanium alloy by choosing a chemistry deposition for that alloy B that allows this to come together without forming these phases that are going to cause failure during building. So with that said, I thank you for the presentation, and I hope you have any time for any questions. Thank you.
There are questions. Si quelqu'un veut poser des questions en français, on peut le savoir. Accélérer tout ça.
Pardon, I don't know French at all, I'm afraid.
Maybe I can start. I have many questions about the presentation. Maybe this is the first